Okay, so looks like some good thinking there this morning. I know it was early and we're kind of just sort of waking up and rolling out of bed and tackling a question like this, but I thought it would be good. This is one of my favorite ones to do on the whiteboard because you're just going to use your knowledge about what's going on to kind of tackle this, and then we'll come up with some ideas on how we can formalize what we're doing here in this lesson. So I asked you to find the highest and lowest point within the curve, and being good calculus students, you guys all thought about taking the derivative. Whether you knew where that was going to take you, you knew this is calculus, chances are we're going to take the derivative. So if we do that, we can get 2x plus 4 as the derivative. And the derivative describes all the possible slopes of the tangents. And one thing we should remember from all of the graphing we did last week is that maximum and minimums are going to occur when the slope of the tangent is 0. Okay, and this was on your test that you did yesterday. One of the questions about saying, you know what, I can find this by taking the derivative and set it equal to 0, because I want to know when this derivative is going to spit out an answer of 0. Because if it spits out an answer of 0, you're either got a maximum point or a minimum point. So if I set this equal to 0, we can do a little bit of algebra to solve and get this number. And what that means is this is a possible maximum or a possible minimum. All right, so because you know it's either going to be the spot where the curve comes and bounces down like this, or comes up and does like this. So I saw that people do that really quickly, and then I popped into your rooms and said, how do you know that this is a max or a min? And we had some great answers. One really good answer is, you know what, this is a parabola, and it opens up, so it has to be a minimum, which is true. Okay, but this is the location of the point. This isn't the value of that spot. So knowing that it occurs at x equals -2, I want to know what the actual value is. And for that, we're going to sub it into our original. So right now, this is a possible, whoa. This is a possible location of a max or min point. Now, the fact we know it's a parabola, we know it's going to be a minimum. But in other cases, if it's a cubic, remember cubics do this sort of thing, or quartics might have a bunch of balances, or quintics. We're not sure if it's going to be a max or a min. But this is the possible location. But what we want to do is actually find the value of that. So remember, the value is the y value. So we do this by going and subbing in f into the, or 2 into the original function. So plugging that into the original function, pretty quickly we can get that the answer is -1. So therefore, -2, -1 is the coordinate, okay? Now, I actually probably won't write the coordinate down because I'll answer this. I'll say this. We think that this is going to have the min value is -1 at x equals -2. And the only reason I can confidently say that this is a minimum value is because of what I know about parabolas. I know this is a parabola that opens up, so this has to be the lowest point. But I'm talking about investigating highest and lowest points within an interval. So if we were talking just a regular parabola, it has a minimum point and no maximum points. But within this, this section of the graph, we could have higher or lowest points within this section. So after we look for where the slopes of tangents are 0, we also have to test these points. And we can test the endpoints of our interval to see what numbers they give us. So I'm also going to test f at -4. And I want to find out if f at -4 is a max or a min, or another point. So when I plug in -4 into the same original equation, -4 squared plus 4 times -4 plus 3, again, we can get 16 minus 16 plus 3. So that's 3. So that's a pretty high point, obviously higher than -1. But let's test the other endpoint. F at, what was it, 1. So f at 1, plugging 1 into the original, gets us 1 plus 4 plus 3, and we get 8. So obviously at this spot, 8 is going to be a higher value than the 3. So it means that our max value is 8, and it happens at x equals 1. And then one of the groups had a little graph. If you go to the Jamboard on the second page there, you can see that someone actually graphed the situation that we have. Let's see if I can get that over here, I think. There we go. So there's the second group, and you can see that they've done a graph here that shows exactly what's going on. It's got this function, and you've tested 3 points. We knew that this one was going to be the minimum, and then we tested the other 2 points and found out this one only goes up to 3, but this one goes up to 5, or 8, excuse me. So that one ended up being the max point. Okay, so a nice little visual of what's going on. All right, good. So this concept is what today's lesson is going to be about finding maximum and minimum points. So I'll give you a second to write this down, but we just sort of summarized everything that we did right there. So this is just a handwritten part of what we just visualized. So the first thing you're going to see me here saying, this is an algorithm for finding the extreme values. An algorithm is a fancy word for a series of steps. So we follow these steps in order to ensure that we can find all extreme values or maximum minimums within a certain interval. So we start by using the calculus side of things, which is we know that all local maxes and mins are going to happen when slopes of tangents are 0. So we find the derivative, which is representing all the slopes, set it equal to 0, and find out the x values of your max and mins. We'll then take that x value and plug it into the original to figure out how high or how low it is, and compare it to the endpoints. So you're also going to plug in the endpoints A and B, plug those into the original, again, because we want to know how high or low it's going, not the derivative. The derivative would tell us the slope of the tangent at those spots. That's not what we want. We want to know the value. And so the maximum of all of those things that you test is obviously, the largest one is obviously the maximum value, and the lowest is the minimum. Since we are doing an interval, we should have a max and a min for everything within that interval. Even parabolas that open up and normally don't have maxes, when we chop it off and say you're only looking at this much, you should have a highest point within that interval. Okay, so we'll do this a couple of times just to get comfortable. So let's do it on a different function here. We're going to find the max and min on this one, f of x equals x cubed, and we'll follow that algorithm. So the first thing I got to do is find potential maxes and mins. I know they'll happen when the derivative is equal to 0. So I'm going to differentiate this. And the derivative of x cubed is 3x squared. And I know that these will happen at 0. So I set it equal to 0. Next, I have to solve for x. So solving for x means getting x by itself. So I'll divide both sides by 3, although I don't imagine you'd write that down. You know that it's this. And then x squared is equal to 0. If I want x, I'm going to take the square root of both of these, which of course is overkill because I think we all can see that 0 is the answer to this. The only value for x that's going to make this work is 0. So that is a spot where the slope of the tangent is 0. That means it's a potential max or min. Let's find the value of 0 by plugging 0 into the original function. So this math isn't going to be too difficult. 0 cubed is 0. All right, so there is one of our values. But let's also check the endpoints. So we're also going to plug in -2 into our function. -2 times -2 times -2 is -8. And plug in 2 into our function, and we get +8. So what this means is of all these values, the highest one is going to be the local max. So which of these is the local max?
8.
The 8. So this is going to be our max value is 8, and it happens at x equals 2. What's the min value?
-8.
Yeah. Wow, the smart board is struggling today. So the min value is -8, and it happens at x equals -2. So I've got a bit of a problem. What happened? I thought that this was going to end up being one of my mins or max, but it turns out it's neither. It's not a maximum, it's not a minimum. There's a point that's lower than that, and there's a point that's higher than it. But I thought this was going to happen. Any ideas? Any suggestions, ideas?
It's a cubic, so it flattens out at the origin.
Right, good. So it goes back to our picture. We think of what this actually looks like. X cubed looks like that. And so if we are investigating slopes of derivatives, this does have a little spot right here where the derivative is 0. The slope is 0. It just sort of flattens out at that spot for an instant, and then it continues on going positive. So the slopes of tangents are positive. They're getting smaller and smaller, but they get here, boom, and then they just keep going positive. So just because the derivative equals 0, it doesn't guarantee that it is a maximum or a minimum. It just sets out a possible max or minimum. We still have to test all the other ones to find out if indeed it is. And we've seen lots of functions that look like this, where it might flatten out for a second, but keep going up. So we have to be aware that they may not be maxes or mins. Okay. And of course, oh, I think I skipped one. Oh no, okay, that's right. Okay, I'm going to give you a second to try this one on your own. All right, so what we have here is a cubic. So we already can imagine cubics, what they look like. They might have a spot that flattens out. They might also have a couple of bumps. We're probably used to seeing those last semester. But let's actually do the math and see if the math can tell us without even knowing what the graph looks like. So first, I'll differentiate and see that the derivative of x cubed is 3x squared, and the derivative of negative 3x squared is 6x, and I'll set it equal to 0. Now, in the first two examples we did, we ended up with a little linear equation that we can solve by getting x by itself. This is a quadratic equation. If you think back, quadratic equations require that you factor and figure out the values, the zeros, the roots. So in this case, I can do a quick little factoring. Common factor seems like the most obvious choice here. 3 is in both, so is x. And so we're going to say x minus 2 is a good common factor. Again, you can always check your common factors by doing rainbow back and seeing if you get the same answer. And we do. Once we have these, we should be able to identify the roots. This is coming back from advanced functions as well. That the roots are, well, this is 3x equals 0, so obviously x equals 0. Or x minus 2 equals 0, and so x equals 2. You probably won't write the first line down because you're so good at seeing roots that we saw, that we did a lot of in advanced functions. So we see that these are possible answers. So we do know that this graph, regardless of what it looks like, is going to have a flat spot at 0 and another flat spot at 2. So the question is, are these maxes or mins? We're not sure yet. So we're going to test them by finding out the values and comparing them to the other values. So we've got to test f at 0. Let's do that one first. 0 cubed minus 3 times 0 squared plus 1. 0 minus 0 plus 1 is 1. Okay, so that's one of my values. Let's try 2. Actually, I'm having a bit of an issue with 2. Can anyone see an issue with 2?
It's outside of the range.
That's right. So if you notice here, I said I want to know all the spots between -2 and 1 that get me maxes and mins. And this one, 2, even though it is a spot where the graph flattens out, or sorry, the tangent flattens out, it's not within our range. So I'm going to have to ignore this guy. Oops. Not in interval. Ignore. So it's not that 2 is the wrong answer, because it is, but in this particular question, it's outside our range. Or domain, I guess. It's outside our domain. It's outside our interval. So I'm going to ignore it. Now, in a completely other question, I might have said between -2 and 5, and then we would consider this one. So I'm not going to even need to find the value because it's not a possibility within this domain. All right, but the endpoints are, so let's put in -2, -2 cubed, minus 3 times -2 squared, plus 1, so that's -8. And then -2 squared is a positive 4 times a 3 is -12 plus 1. And I think that gets me -19. So that's a pretty low number. Probably going to be my min, but let's find out. F at 1 cubed minus 3 times 1 squared plus 1. And that's 1 minus 3 plus 1 is -1. And so now just comparing all the values, I see that the highest of all these values happens at 0. And so the max value is 1, and it happens at x equals 0. And our min value has to be this guy. Min value is -19, and it happens at x equals -2. And so again, I can check this graphically. Sorry, plus 1. So we look here, and the graph does tell us of a couple of spots. We can see those 2 spots that we knew about. We knew that we were talking about 0 as a possible spot where the tangent flattens, and 2 was a possible spot as well, but that's outside of our range, or our domain, excuse me. So I only asked for the stuff between, what was it, -4, no, -2 and 1. So I can put that on here. -2 is less than or equal to x, is less than or equal to Oops, that's going to equal to 1. Sorry, what range was? Yeah. And so we're only investigating this part of the graph. And so yes, the highest or the max value within this little range is 1, which happens at 0. And then the minimum value actually ends up being way down here at -2, -19. Okay. All right. Okay, let's look at this one. So again, a situation where we have some sort of real life situation where, in this case, a flu breaks out and it spreads around the school. The modeling suggests that it spreads in this equation. So again, how you come up with these equations aren't what we're talking about. We're just saying someone has modeled this scenario and predicts that this is how the flu is spreading, which is going to tell us how many people have it after a certain amount of days. So what we're interested in doing is finding out within that first 10 days, which are the problem days. So this is something that's happening right now. Lots of mathematical modeling going on right now with COVID models to try and see how things are going. You'll see lots of exponential curves in those ones, but they want to know when are these maxes and minimums taking place so we can make sure that all the resources are available. They can predict those days that are going to be the troublesome days. And once, maybe we can, if we do the lockdown stuff we're doing, we see that it comes down. So where are those max days? When can we be most prepared? So that's the math that's happening right now. The hard part is coming up with the model. The easy part is doing the analysis of that model, and that's what we're doing here. So here's a model that's going to represent this scenario. But for us, all we're going to do is do the exact same thing we did before. Find out when the potential maxes and mins are going to be by taking the derivative of this and setting it equal to 0, and then testing the endpoints. The difference is, of course, the equation's a little bit more difficult, but something that we've had lots of practice doing already. I guess it's f at t now. So f prime at t is a quotient rule, right? We've got a quotient here, so we're going to have to differentiate the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. So the derivative of the top is 64 times the bottom, 4 plus t squared, minus the derivative of the bottom, well, the 4 is going to be gone, so it's just 2t on the bottom times the top, all over the bottom squared. We can tidy this up a little bit by rainbowing the top. Actually, I'm going to bring that negative together. So I'm going to rainbow a negative 2y or 2t. Oh, there's not really a rainbow happening, isn't there? Sorry. But we can do this. 64 times 4, 256. Plus 64t squared minus 128t all over 4 plus t squared squared. Now remember, we are using this derivative to find the values that are going to be 0. We want to know when the slopes are 0. So we're going to set this whole thing equal to 0. Good news is our question becomes a little bit easier because if it's set equal to 0, the first thing I can do is take this number and bring it up and multiply. But since I'm multiplying by 0, it's just going to be 0.
Mr. Lee?
Yep.
Isn't it 128t squared?
Oh, good, thank you. Yep. So when we're going to bring that together, then we're going to have 2t squares. Thanks, Jacob. So we're going to have the 256, and then 64 minus 128 is going to be minus 64t squared. This is another quadratic, which we would factor, but we only have one t value, so we can actually solve for t. When you only have one t value, you can still solve for t, even though it's a quadratic. So we can do that by isolating for the t, bringing this over, make it negative 256 equals negative 64t squared. Divide both sides by negative 64. And that's going to be then 4 equals t squared. And if I want t by itself, I take the square root of both sides. And one little heads up, remember when we're taking the square root, we should remember that there are two possible answers. A positive 2 squared would get you 4, and a negative 2 squared would get you 4. But in this particular case, the negative 2 doesn't make sense. That would suggest a negative time. Okay, then it's also outside of our interval. So we're going to ignore negative 2. But we do know then that on day 2 is a possible max or a min, because that might be, it is a spot where the graph is going to flatten. Now what we have to do is check the endpoints. Now I didn't give you an interval specifically in this question, but I did mention there we go. I did mention that I want to know the largest number of people infected during the first 10 days. So we know that day two is a possibility, but we should consider the endpoints in the first 10 days. That means I've got to check f at 2 as a possibility, f at 0, except 0 you know is going to be 0, and f at 10. So very quickly I'll substitute those into the original equation. 64 times 2 plus 4, or over 4 times 2 squared. So that's going to get me 128 on the top. 2 squared is 4, plus 4 is 8 on the bottom. So there are 16 people infected on day 2. What about day 10? 64 times 10 over 4, oops. 4 plus 10 squared is 640 over 104, which is 6.15 people. And I guess I should just at least somewhere say, I also checked the 0 spot and put 0 in and got that. So from this information, the troublesome day is day 2. So the max number of people infected is 16 on day 2. So what this tells me is this flu is very, very quick and people can recover relatively quickly. And it's not really that, doesn't really spread that badly. Now, this is normally where we would end with this day as just finding some max and mins within some functions. But the idea of finding a maximum and minimum has a really great practical application. And normally we would spend a whole day doing practical questions about finding maxes and mins. It's probably the biggest application of calculus in the real world, is finding maxes and mins. We want to know what the extremes are. So if we're building a bridge, we want to know what's its maximum that it can hold. What's the minimum can it hold? Economics. So the reason why lots of people or lots of programs that are interested in economics or finance ask that you do calculus is finding max profit and min profit and things like that is a big deal. And knowing when it's going to happen is huge. So we apply calculus to financial problems all the time. Okay, it's another big one. Everyone thinks they hear calculus, they think engineering, and that's the only spot. While it's huge there, obviously, it gets modeled everywhere. So we're only going to do one max-min problem on top of this one, just because of the sake of time. And we're going to look at this one. And the reason I chose this one of all the different ones is because it harks back to a question that you answered in grade 10. And this is where you start to realize that in grade 10, when we did quadratics, we answered optimal questions. Find me the best shape. Find me the biggest profit. Remember, you answered questions about if I increase tickets price by a little bit, I'm going to lose some sales, but I'm going to make more money. What's my maximum that I can do? All of that is, we can answer when it's a quadratic, we can answer finding the vertex. But the calculus allows us to find vertex much quicker. Okay, so this question isn't part of the max-min lesson. It's an addition to it. It's just an optimization one, but it does use the same concept. The only difference between this question and the ones we did before is there's no interval. Okay, so I'm looking at all the possible scenarios. So hopefully you've been copying this down as I've been rambling. And it's talking about a rectangular field is to be enclosed by 300 meters of fencing along 3 sides. The fourth is a river, so you don't need a fence on the river. Determine the dimensions and area that will maximize the area of this field. So in grade 9, we actually answered this question by having an enclosed fence and finding the biggest area, the optimal rectangle. We might have remembered back in grade 9 that the optimal rectangle was a square. A square was the one that gave us the biggest area for the minimum perimeter. In grade 10, we upped the level of difficulty of that question by saying you don't need all sides. So in this case, we're taking away one of the sides, and the shape is no longer going to be a square. Let's figure out the optimal shape for this. So the beginning of this is going to feel just like what we did in grade 10, but the end will be calculus instead. All right, so what we don't know is the dimensions of these fields. We don't know the length and the width. So we're going to make those our variables. So I'm going to start by calling the width x. Well, I guess, I don't know how you're imagining it. I imagine that the width and this the length. And I'm going to call those sides x. And since it's a rectangular field, it says it has to be a rectangular field. I know that both sides are going to be x. Now you could cop out and say the other side is y, but I know something about the other length. So if I have 300 meters of fencing, and I know I put x here and x here, how much do I have left over?
100.
Why 100?
Does that make it a square?
Okay, now when we take away one of the sides, the optimal is not going to be a square anymore. Okay, but if it works, you'd be bang on. But because we've taken it along one of the sides, it actually changes the scenario a bit.
Would it be 300 minus 2x?
Okay, there we go. So If this was 10, let's say it was 10, so it was 10 and 10, we've used 20 meters of fencing. How much do we have left over? We have 300 minus 20, and the 20 comes from these two. If it was 50 and this was 50, we would double that and get 100, and it'd be 300 minus 100. But these, we don't know how big they are, so they're x and x. And so that's correct in saying that this side is 300 minus 2x. And what we want to do is maximize area. We want to maximize the area. Which means I have to consider a formula for area. So area is length times width. But in this particular case, the length is 300 minus 2x, and the width is just x. So if I multiply these, I can get a formula that will represent the area. So rainbow the x, and I get 300x minus 2x squared. And I have now a formula that represents the area. The maximum area, the max area, will happen when the derivative is equal to 0. So this model here represents all the different areas. So if we had a really skinny yard, it would be a small area. As you increase it, it starts to get bigger. The area is going to get bigger, and then you're going to get bigger, and then you're going to hit that maximum area, and then you're probably gone too far to make it too skinny, and then the area starts to dip off. So I want to know when this is equal to 0. So I'm actually going to put all this in blue, because I haven't done the calculus yet, but I can do a prime as the derivative of area and say, okay, 300x, the derivative of 300x is just 300 minus 4x. And I know the max will occur when this is equal to 0. A little bit of algebra. 300 divided by 4 is 75. So my maximum is going to occur when the width is 75. But remember, it asks for not the width, it asks for the area. And so this is just like what we did before. I now take my value and plug it into the original function. The original function being this guy. So if x is 75, the area is 300 times 75 minus 2 times 75 squared. So 300 times 75 is 22,500. And then 75 squared times 2, or negative 2, is negative 11,250. And subtract these, and I get 11,250 meters squared. So that is going to be the maximum area. The only thing I'm missing is the dimensions. So my last step is to say, well, I know this part is 75 and this is 75. Then I got to figure out this number here. 300 minus 2 75s is going to leave me with 300 minus 150, 150 meters as the width. So now I know that the max dimensions are a field that is 75 meters by 150 meters, and max area is 11,250 meters squared. So really, the word problem part of this is all to get a function. And of course, if we had more time, we'd be spending a whole day on different types of problems that would end up with different functions. Okay, so like there's other ones where we'd be talking about different maximums, we'd be talking about financial stuff and things like that. But all of the word problem part is to get to a function. Once we have a function, it behaves exactly like the first stuff we did. Set the derivative equal to 0, or find the derivative, set it equal to 0, get your values, and then figure out your x value, then figure out the y value to figure out the max or min. Now in this case, we should see that it is a minimum because this is a parabola that's upside down. Okay, you can see that there. And there's no endpoints on this, so that has to be our max value. Okay, so the little bit of practice that you could do with these questions, the questions on page 200 are just max and min, like you started off with in the warm-up. The question does say to graph it afterwards. We're not going to graph it, just go off and find the max and min within the interval. And then page 206, number 3 is like the one we just did. And number 4 is one that we skipped. If you want to see another example of that, then you can watch my video on Unit 3, Day 5B on YouTube that talks about number 4. But anything I'm going to ask you to do would be just like number 3. So number 4 is just purely optional. Now, while these are practice questions, I would imagine most of you will spend your next bit of time talking about or tackling the last 2 questions on your assignment. So let's just go and remind ourselves of the assignment. Again, you can't see all of this, so yesterday, the first part we did, or I guess 2 days ago, we did velocity and acceleration, so that was number 1 and 2. Yesterday, we handled questions for number 3 and 4. And then today, you can see one just like your warm-up and one with an area question just like that. Okay, so this is going to be your number 1 priority. You might only have these last 2 to do, which is fine. You can do them right now. If not, you have period 4 to finish up this assignment. Okay, so again, I'm going to give you a time to do a little bit of work and a break, and we're going to come back at 10:15 to do our next lesson. So unless you have any questions, you're welcome to leave, and I'll see you at 10:15.